Hi, let me introduce myself. My name is Artem. I wrote my first C++ program 20 years ago. I was a lab assignment at the university, first year. And it looked a lot like the right side of this picture, which is also quite old, from 2008. But I wrote my first program 4 years before that. I still remember my professor, Karamova Lyudmila Mikhailovna. She was like scratching her head and raising her brows a lot. Oh, since then, a lot more C++ code. And the first Stockholm C++ meetup I attended was 6 years ago. And since then, I'm semi-regularly attending these meetups. I'm hooked. I work at Leica Geosystems in a team that writes C++ libraries that are shared between different products in a company's portfolio. And there I'm also like, it's 8 years already. Time flies. The company is working in the fields of geodesy and heavy construction. So the products are like total stations. These are measuring devices that land surveyors are using. And there are special systems called machine control that are installed in heavy construction equipment, like excavator here, that helps the excavator operator to guide their excavation according to the digital model. So the libraries we write, they are like they run from embedded devices to cloud to desktop. I also maintain an open source library for constrained Delaunay triangulation, quite unimaginatively called CDT. And this library was also born at Leica Geosystems, but then the management gave us permission to open source it. So since then, I'm the main maintainer of this library. And this presentation is about that library. So you can expect from me to introduce you the Delaunay triangulations. What are they? Do some brief introduction of the library. What can it do? And then there's going to be a bunch of stories and slides quite loosely connected to each other, but hopefully somehow coherent. And they will discuss technical and non-technical topics related to the CDT library. So after this talk, I expect you to get some idea about triangulations, if you don't already, and about the library. Maybe there will be something interesting to learn or discuss, suggest, criticize. You're free to nod along or shake your head in disapproval. I expect you, well, I mean, I hope you to enjoy the presentation, but if you don't, please feel free to mark it as boring in the survey, which I'll give a link to at the end. So a quick show of hands. Who of you have heard of a CDT library before? OK, that's good. So like a lot of people to disseminate. Right, who of you have heard of Delaunay triangulation? That's more, but still there are people. Good. So I'll start with the completely made-up fantasy story as like a hook. So it's in the past, let's say early 90s, late 80s, and you're a land surveyor, maybe in some hilly country, let's say Switzerland. And like very rich customer approaches you and they say, we'll pay you handsomely if you can measure the surface area of the pastures that we use for our cows to graze. But you have to do it very accurately, otherwise we'll not pay you. So you come back to the office and you think, what can I do? I mean, it's like 90s. We don't have all this fancy technology like photogrammetry, drones, and laser scanners. And what you can do is to measure a bunch of points and then connect them in triangles and then calculate surface area of each triangle, add them together, you get some good enough approximation. So you do that. You go to the fields, you survey for the whole day, you come back and you manually connect the dots, rushing it, want to see the result quickly, and then you get something like that. And you think, that's suboptimal. Maybe that's not as accurate as I hoped. You think, and then you're ready to like pick up the phone and call this customer and say, I can't do this job. It's not going to be accurate enough. But in the evening, you go for a beer or coffee, and a friend who is both smart and by coincidence very good looking tells you, have you heard of this thing, Delaunay triangulations? They're great. You should try that. Delaunay triangulation, what? You run to the library, right? There's no internet. And then you study it, and then you connect the triangles, and you look at the result. That's so much better. You give this to the customers. They are so impressed. They pay you. Then at the end of the year, you win the Surveyor of the Year award or something. Happy ending. Right, so hopefully this will motivate you somehow to learn about the CDT library. In a nutshell, it's a C++ library. It generates constrained Delaunay triangulations, hence the name. It's open source under Mozilla public license, cross-platform, tested on main desktop systems, but should run on other systems. Why not? It's backwards compatible to C++ 98. Has no external dependencies, means like the dependencies it has are included in the source. Performant-ish. I mean, it's been profiled and the bottlenecks were removed. So maybe it's not the fastest out there, but it's fast enough for most of the tasks. It's numerically robust, so it relies on these things called robust geometric predicates. More on that will follow later. But this means basically that you have a guarantee of correctness. If your input is correct, you will get the output that's correct. And it's quite flexible, so it can be consumed either as a header only or as a compiled library. So what's the Delaunay triangulation? It's a triangulation. And the triangulation of points is when you take the points and you connect them into triangles. And Delaunay triangulation is a good kind of triangulation. So it is, one might even say it's the best kind of triangulation, but it's according to a certain criterion. So it maximizes the minimum angle of the triangles. That means that you get more regularly shaped and basically nicer looking triangles, but also less close to being degenerate. So like not having very sharp angles, not having very large angles. That's convenient to have for tasks like interpolation. There is a comparison at the bottom, sum triangulation and versus Delaunay triangulation, so you can see the difference. How does it achieve that optimality? It uses something called Delaunay criterion. It says, like, basically, each triangle's circumcircle should not contain any points in it. So here's a good example. It's a very simple triangulation, two triangles. And if we draw circumcircles, which are the circles that go through the vertices of the triangle, there is no other vertices inside it. So like in this example, point B is not inside the red circle of a triangle ACD, and the point D is not in the blue circle, which is a circumcircle of a triangle ABC. So that's not a Delaunay triangulation, because if we move the point D slightly inwards, keeping all the same edges, it's going to be inside the blue circle, right? So how can this be fixed? There always exists a Delaunay triangulation, so what we need to do is to flip the edge, and then it's Delaunay again. What is it that CDT as a library can do when it comes to the Delaunay triangulations? I mean, it can give you the basic Delaunay triangulation of the point set. There is also something called constrained Delaunay triangulation, which is kind of, it's not a Delaunay triangulation because you tell it that I want some edges connecting certain points to be in that triangulation no matter what, even if it breaks the Delaunay criterion. So this way you get this edge, this long edge on the left of the A, like compared to the previous slide, you see? You get this edge, but the triangles adjacent to this edge are not Delaunay triangulations anymore. There is also something called conforming Delaunay triangulation, and that's preserving the Delaunay criterion, but it introduces new vertices in the triangulation to achieve that. So you can see there were two new vertices added, and this way you can have both the edges and Delaunay triangles. What happens if the edges intersect? Well, they shouldn't, ideally. So the default mode, the way the CDT handles it, if some edges intersect, you'll get a runtime exception saying your edges intersect. This and that edge intersect. If you want to resolve these intersections, there is a mode, and it's called try to resolve because it doesn't have the correctness guarantees, but it works most of the time. And it does add new vertices at the position of the intersection of the edges. And the third one is kind of a legacy. I'm thinking about maybe removing it. It just skips the checks. It's like if you're sure that your edges don't intersect, you can just tell it, don't check. It will be maybe a little bit faster, but if the edges do intersect, it's like undefined behavior. I mean, you get either an error or wrong triangulation. That's how resolving the intersections look like. So there are two edges. You insert the new vertex where they intersect. This way you can handle the intersecting edges. CDT, the library, handles some corner cases. This is the corner case where an edge is going through some vertices. So in that case, the actual constraint edge is a single edge going from the leftmost to the rightmost vertex. So the library is, the algorithm is correct enough so it's able to detect that the edge is actually there in the triangulation because there are two vertices exactly on it. So you'll get the right correct triangulation with 3 edges actually. It also handles exactly overlapping edges. So you see at the bottom there is like 1, 2, 3, 4 rectangles overlapping. So it's also able to resolve that properly. And it can automatically detect boundaries and holes and remove triangles outside the outer boundaries and inside the holes. And it supports arbitrary topology. Like I'm talking about an island in a lake, on an island, in a lake, on an island, in a lake. Yeah. So a quick walkthrough of an algorithm. It's an incremental algorithm. It means you start with something. In that case, it's fancily called super triangle. And then you add vertices to the triangulation one by one. After you've done adding vertices, you add the constraint edges. So you force them into the triangulation one by one. And finally, you decide what triangles to keep and what triangles to remove. So super triangle is basically a fancy name for a very large triangle. It should be large enough to contain all the points of the triangulation. That's how it looks like in this case of A. You see that? Then you start inserting vertices. So let's say we want to insert vertex V in this triangulation. First thing you want to do is to find near or ideally nearest neighbor in a triangulation. You pick a triangle that's adjacent to this vertex, and then you do something called triangle walk. The way this triangle walk is working is that it checks the edges, and in that case, the point V is on the other side of the HE. That means you go to the neighboring triangle, which is HEG. Then you check again. Point V is on the other side of HG, so you do one more step. And that happens to be the place, the triangle containing the vertex. You found it. After you found the triangle, there's 2 ways. If it's inside the triangle, you do this. You split the triangle in 3 triangles, and then you continue ensuring the Delaunay criterion. If the vertex is on the edge, you split 2 triangles into 4 triangles. After you've done that, you make sure these new triangles are Delaunay. And if they aren't, you do the edge flips until there are no more triangles that are not Delaunay. How does it work to add a constraint and a fixed edge in the triangulation? Let's say we want to have an edge between A and G in there. First, we find all the triangles that are intersected by this edge. We remove them. We have 2, they are called pseudo-polygons. I mean, they're just polygons. I don't know why pseudo. And then there's a method that quickly triangulates them. So you end up with this. And these triangles are not Delaunay triangles, again, just to make to bring the point home. So if you want to conform to the triangulation, what CDT does, it just takes the midpoint and inserts it in the triangulation. And if the A edge, for example, is not there, then you do it recursively until the edge is in there as the sum of its parts. Final step, finalizing or just removing the triangles you don't need. So that's the leftmost image is not finalized. Then you can do the following. You start from the triangles that are, at least one of the vertices is a super triangle vertex. And then you do a region growing, so like spreading to the neighbors until, oh wait, I skipped one. So not finalized, the simplest is just to remove every triangle that has a super triangle vertex. And that gives you the what's called erased super triangle. It's a convex hull of the point set. A convex hull is like a fancy term, but it means like, imagine your points are nails on a wall. And then if you take a rubber band and you put it around these nails, then it will be in the shape of a convex hull. That's what it is.
Sorry.
Right?
If you just have a cloud of points that you measured, how do you know what's inside and outside?
So you know that super triangles vertices are always outside everything because super triangle contains everything.
But if this would be a measurement from a landscape,
yeah,
then
the super triangle will be larger than that landscape.
But what are holes in? If these are the points that you have just measured in a landscape, you don't know what is inside and outside. It's just a big mesh.
So are you asking about the removing of the holes?
Yeah, in this particular case, this A here.
Yeah, so that's, I will get there, or,
okay.
Right? So you can start from this super triangle vertices and you just grow it until you meet the boundary. That's the erase outer triangles. That's quite easy to do. And then what you want, if you want to auto-detect the boundaries, it's kind of a clever trick. And I haven't seen other libraries doing that before, so I'm quite proud of it. But probably, it's quite a simple idea. But you kind of do layer peeling, right? You calculate the depths of each layer. So you start growing until you meet the boundaries. That's the layer of the depth 0. Then you start with the triangles that are across the boundary, and you again grow. That will be the layer of the depth 1. Then you grow it again, 2. And then in the end, you just remove every layer that has a depth that's even, right? 0 to, starting from 0. So like the outside of the A would be 0 depth. Then A itself would be 1. Then the hole in the A will be 2. It will be also removed, and then you continue. Well, I mean, obviously, this requires the boundaries to be watertight. If they aren't, this will not work. Does it answer your question?
My question was a bit different because you started with an example of sampling points in a landscape, but that would never give you this, right?
Right. If you just have the landscape, you don't really need the last two versions. You just need the first one, probably, just the convex hull of the measured thing. But if you measure it, like let's say there's a parcel boundary, and you measure only points inside that parcel, or maybe there's a lake in there. You can add the lake as a constraint, and then you can remove it. Yeah. There is this core values thing that I picked or stole from a Brian Cantrell talk. He likes to talk about this. So like every software has this set of core values that they think are the most important ones. And then when choosing the software, you just choose the software that meets your core values as a user. So there's a bunch of things, and I thought about this, and these are what I think are the core values of the CDT library. They're composability, debuggability, maintainability, performance, portability, and robustness. And why these values? So I think for a tool to be really good, it needs to have the following properties. It needs to do its job well. So in our case, that needs to be fast. It needs to be correct, like robust and portable. Then it needs to be easy to use. So then composability and portability are important. And if the tool breaks, it should be fixable. And if over time you have some ideas how to improve the tool, you should be able to do that. So that's when debuggability and maintainability are important. So then the following big chunk of the talk, I will just use this as a kind of a map for the various topics, and I will just go along different core values and tell different stories about them. Right? So performance improvements. Whenever you can measure the performance, you should, and it's always better to have the actual data instead of a speculation or guesswork on what is slow in a program, in my experience. So I use this pairing of tools that works really well for me, that I like. It's Google Performance Tools and Brent and Greg's Flame Graphs. I compile the library in release with debug information, so for profiling purposes. And then the nice thing about this setup is that can be done non-intrusively, so I don't need to do anything in the compilation process. I can just preload the shared library, provide my parameters as environment variables, and then this will profile the executable called benchmark in this case. And then I can convert this output into something that the flame graphs can understand. In between, I have a grep call, which is nice to have. So like if you're interested in some particular function, you can grep for it. And then it produces the SVG file. And that's how this SVG file looks like. It's a really nice file because you can just open it in a browser, right? And when you actually understand what it shows, it's quite usable. So in this case, what do we see here? We see this like two towery looking structures, one on the left and one on the right. These are boost geometry. And you can see like the higher it, basically what this graph is, on the x-axis you have your runtime, duration of the time the program took to execute. And on the y-axis you have call stacks. Sorted and placed next to each other. So the higher it is, the deeper your call stack is. And then the call stack depth of boost geometry is insane. I mean, this is probably, this is probably some standard library stuff. It's also quite deep. The rest is just like, this is the code of the library, and this is boost geometry, and this is boost geometry. Oh. But I mean, this doesn't really tell us much about the performance. It's just an interesting observation. But what tells us about the performance is that this one is really wide. And that means it takes most of the runtime. So that's probably the bottleneck. Yeah, it's like looking at this gives me this feeling. I mean, it's a monstrosity. When it was just released, there was like a wave of criticism in the game development community towards boost geometry. And I think it was not really fair because, I mean, it has also its merits. It's really nice and it's really generalizable. So for example, I used boost geometry for 4D line simplification thing. So, yeah, I mean, it comes at a cost. So boost geometry R3, what we used here for keeping the points so that we can quickly find the nearest neighbor. And it was the bottleneck, and it was replaced with the simpler implementation of the KD3, which was both faster and, yeah, it removed the big dependency, which is boost. Yeah, again, flame graphs are great. They're really useful for finding the problem. They're interactive, so you're kind of investigating your data, drilling down, zooming out, figuring out what's wrong. And they are shareable, which is, I think, is a great plus. You can share it with a colleague. You can both look at it, and then you can exchange, like, what do you think can be improved? So who uses flame graphs? Just who doesn't try it? I mean, and also it's available in JetBrains products, but they don't allow you to export it for, at least last time I checked, which kills the shareability. I think maybe that's something they need to do. Robustness. So there is something called geometric predicates, and predicate here is in a little bit more general sense. So it's not producing Boolean as a result, but enumeration. And in geometry, the predicates are things that you take the geometries and you make some, classify the way they're arranged towards each other. So on the left, there's an orientation predicate, and it tells you whether the point C is on the left, exactly on, or on the right of the line that's coming through the points A and B. And in circle predicate, it tells you whether the point D is inside, exactly on, or outside the circle that's going through the 3 vertices A, B, C. So these are the predicates that are used to make decisions on how the triangulation algorithm proceeds, whether it flips the edge or not, where the point is, in which triangle the point is located. You have seen this before. So the problem with floating points is that they are subject to the rounding errors. So these predicates will not always, if you do it naively, it will not always guarantee you the right result. And of course, you can do go higher precision, like a long double or something, but or even, what is it called? Long double? When you do arbitrarily length numbers, a long number, what's it called? You can do big numbers, basically but this is very slow. And the trick is that there's adaptiveness to this algorithm. It tracks the error, and if the error is large enough that it can affect the outcome, so to flip from left to right or from exactly on to the left or to the right, then it extends the precision. So by taking the remainder and putting it in an extension, and also and it does it in 3 steps, I think. So that kind of gives you both speed and exactness. The speed you get because in 99% of the cases the error is not large enough, but when the error is large enough, then you get the exactness. So this is nice because you don't need tolerances anymore. You don't need 1e minus 6 things. And it gives you strong guarantees of correctness. But it's so pedantic. It's annoyingly pedantic. Sometimes you see 3 points and you think, oh, they're on the same line. No, not to this predicate. I mean, it will make a very, very narrow triangle there because they are not exactly on the same line mathematically. Well, it's a trade-off. Also, something that improves robustness is a coverage-guided fuzz testing. I've heard about it. There was a nice talk on the C++ meetup about it. I never used it. But once upon a time, there was a user on GitHub called someone else and says, hey, I found these bugs in your library with fuzzing. And I looked at the bugs, and one of them was an extreme corner case, still technically a bug. The second one was a genuine bug. So I thought, oh, this is really interesting, and it works great. And I reproduced this setup, and I also did the fuzzing myself. It's surprisingly good at finding the things you have never thought about it. And this user made a nice write-up about this, how he fuzzed the library, so you can read it at this link. So this is the corner case bug, by the way. It's an interesting exercise. So this is the code that calculates the super triangle vertex coordinates. It takes some upper bound of the in-circle radius, which is calculated from the bounding box, width and height, the maximum of them. And then it uses this maximum width, either width or height of the bounding box to offset the center of the bounding box coordinate to calculate the y position of one of the super triangle vertices. And the input that triggers this bug is here. So it's 2 points, one with x coordinates 0, y coordinates huge number. And the second point is x coordinate 1, y coordinate huge number. So anybody has an idea what can go wrong here? Are you still parsing the slide, or you don't have an idea? No guesses?
There's not enough precision?
Yeah, It's a rounding error. So your R will be, so you choose bounding box width would be 1. Bounding box height would be 0, because it's the same, exactly the same huge number. So R is 1. And if you add 1 to 1 in the power of, like, to this huge number, it's just going to be the same number because of the way floating point works. So yeah, I mean, it's a bug. I mean, technically correct is the best kind of correct, right? But I fixed it in a very dumb way. I just until this is the same number, I just multiply the R by 2. It's not likely to happen. I don't think so. Right, but when doing this fuzzing, what it gives you is some kind of input that triggers the problem. And it's generated by this genetic algorithm. So it's kind of jibble-jabble kind of input, right? And sometimes it's quite a big input. And I had this great idea that then I used later, and I just want to share it because I think it's a really good idea, that you just automate the minification or reduction of the input to the reproducer. So it finds the smallest subset of the input that still triggers the problem. And I mean, I don't know how about you, but quite often in a bug ticket, right, there is this huge file attached, and then you spend half a day just pinpointing where the problem is in that huge file. And since it's huge, it's also slow, and yeah. So what if you just had it magically reduced to the place where the problem happens? I wish I discovered it earlier, really. And the way it works is first we take the inputs and we remove edges one by one, and we check if some condition still holds, if it crashes or an exception is thrown, or just something happens. And then after no more edges can be removed, you start removing vertices from the input one by one. And when you're removing vertices, you should not forget to remap the edges as well. And then when you have this working, you just hit run, and then you go for Fika, and you come back and you have a nice, small, reproducible reproducer. I mean, that's great. Composability and portability. So, show of hands. You have a library, and there's a user, and it says, I really need C++ 98 compatibility. Can you do it for me? Do you politely decline? Who politely declines? Who agrees? Who declines not politely? Right. Well, I mean, it's a trick question. This user is my employer. So, I mean, I have no choice. So we have to comply. Actually, it's not C++ 98. It's C++ 03T technical report 1. But, I mean, that's how I see this picture. It's the same thing. So if you have TR1, you should have 98. Why not? Yeah, so the way it's done, it's polyfills. And a polyfill is something that you have functionality that's in the later versions of the standard library. You just implement it for the older compiler yourself. And you check if the compiler is old, you just use your fallback implementation. So it's not great for the code readability, but I mean, okay, the slide is skipped, but thanks God Boost exists, because Boost really helps in here. Without Boost, I don't know what I would do. And that brings us to the next slide. So the library has minimal dependency. The only dependency that's embedded by default is this robust predicates. It's quite advanced bit level magic, so I didn't write it myself. I took one that was readily available. It's a single header bundled in the code, and it's great. I mean, only if you need C++ 98 compatibility, you need Boost as a dependency for all this glorious polyfill code. And minimizing the dependencies like that is a trade-off, right? You are more portable. It's easier for the user to use your library. But sometimes you have to, instead of taking some good solution from somewhere, you have to reinvent the wheel. Or, I mean, great artists actually steal the wheel. So I'll have some story about this later. And It's easier, of course, to achieve if your library is small, which is the case for CDT. So I think it works here. It will not work for everyone. This is some nice thing I wanted to show. So if the user have their own types for the points and edges, which of course they do, I mean, it's nice not to force them to make a temporary buffer that they have to copy the data in so that they can just feed it to CDT library, because the API of the CDT takes a pair of iterators always. So there is something you can do. You can provide getters for the x and y value of the point as a function objects. So it's kind of a customization extension point, which is if you want to make users' life easier, that's one way to do it. So yeah, in this code, I'll just go through the point. You see the very first line, your point is just a array of two doubles. And the getters are just returning the first and the second element of that array. Inside the CDT, it's still CDT types, though, but it's just like to avoid the copy. There are some more features. There is Python bindings available. It's integrated with VC package and spec. I've never heard of spec, but some contributor implemented apparently a spec package. Conan. It's interesting because I use actually Conan file for continuous integration, but Conan doesn't have it, and I don't want to do it myself. So if somebody wants to do it, yeah. And then it can be either header only or compiled by doing some tricks in the code. It separates the template code in a declarations and implementation file, and there is a if-def, which says if it's header only, you include the implementation inside the header. If it's not, they are separated. And then if they are separated, you also have the file that explicitly instantiates the things. So I wanted to ask you, do you have strong preference, actually, when you consider a dependency, whether it's a header only or compiled? Who has a strong preference for header only? Who has a strong preference for compiled? Who doesn't care? Yeah, that's what I thought. I think it's already done, but it's makes the code less conventional, and it's all these tricks you have to do. And yeah, I think most of the people just don't care. Yeah, maintainability and debuggability. It needs to be also fun for the author to work on a library, and it's also, if the library is debuggable and maintainable, the speed increases. You can fix the bugs faster. You can implement new features faster. This is one point I have. It's very subjective, but I think indices are superior to iterators when you are talking about vectors. Just they're a better option. Because no iterator invalidation problems when the vector resizes. You can use the same index to address multiple vectors. In the case you decided to do like a, what is it called? Structure of arrays, yeah, approach, exactly. The indices can be made smaller, like they can be made 32 bits. That's the case for the CDT. By default, it uses 32-bit indices. Because I just did the math, and I looked, what should be the input size if I need to address more than 30 bits, and it's a lot. So probably if you have this kind of a scale problem, it's okay for you to flip the switch, flip a CMake flag. Yeah, and indices are nice for debugging because you can label things right in the visualization. Like this is vertex point number 0, this is point number 1. Right? About the testing of the CDT, it's kind of, again, it's the case that's true for this library. It's not true for any other library. But because we have deterministic behavior and because we have correctness guarantees, we should always produce the same output for the same input and a set of parameters. So it's a good fit for the data-driven tests, which means that we have textual formats for inputs and for outputs. They are nice because they're also diffable and human readable. And the tests are just take the input, take the settings for the triangulation, run it on these inputs, produce the outputs, compare it to the expected outputs. So a test has a text file that's input, a text file that's output, and the code sets the parameters, takes the input, produces the output, compares if they're the same or not. And that works really well. And it's like good bang for the buck, right? Because you just write little test code and it kind of sets the behavior in stone on this particular data set. So it's kind of nice. The way the error handles, there are asserts everywhere in the code, so it's kind of heavy-ish on asserts. And exceptions are helpful in a sense they help you to pinpoint the problem. If there is an edge intersection, it tells you which edges intersect. You can see here also, like try to do this with iterators. Duplicate vertices, if there are any. Duplicate vertices are not allowed in the library. But we provide utilities to check for duplicates and fix the duplicates and remap the edges. There is a tool I wrote that visualizes the output. I'll quickly show it to you. So I can step through the algorithm. I can add the points one by one and see how it looks like. The last point is always highlighted in red. I can step through the process of adding edges, and I can draw the indices, and I can pen and zoom. And I can change the settings here. That tool helps me a lot to quickly go from reproducer code to the bug fix, and also for testing, visually inspecting things. There is also an online prototype in this link. It's kind of a toy project with ImGUI and compiled to WebAssembly with Mscript. And you can play with it if you want on that link to get a feeling. Right, so determinism is important. Imagine you write a table tennis game that's based on physics, and you're naive enough to just take the elapsed delta time and use it in your physics update step. This will make your physics not reproducible, and it will be really hard to pinpoint the bugs and reproduce the bugs. So instead, you lock your time step, right? So it's kind of the same when it comes to this library. If you have deterministic behavior, it's much easier to debug. A lot easier. So, and I define determinism is that running on the same inputs, the program will always produce the same outputs. Do you think this std_ends element is deterministic? Is it? Who thinks yes? Raise the hands. Okay, yeah. It's not stable, right? It's like sort. It's not stable. So for this code, I have little time, but basically, depending on your standard library implementation, they treat it differently. And there is no stable ends element in a standard library. I think it's an omission. Because they're so tightly coupled with the sort, std sort. So you have stable sort, but you don't have stable ends element. Why not? I don't know. C++, I guess. So what I did was also kind of ugly, but I just ripped it from the libc and included it in the code. So I always have the same implementation. Random number generation. Also, why is something like split mix 64 is not in the standard library? I don't know. It's a very simple random number generation, pseudo-random number generator that fits on a slide. And it's faster. It has much less state, which is important if you don't want to have it static, and initializing it is not costly. So you can just always seed this generator with the same seed inside your API, and you get deterministic pseudo-random number generation, always the same sequence. When it comes to promoting the library, I didn't do much. I asked for stars in a README. I did some GitHub CEO. There's a nice article about this. GitHub, actually, when you search for some keywords and you don't sort by stars, it has some algorithm which basically defines the weight of these keywords in a name of the repository and about section of this repository. So if my keywords are constraint, Delaunay, triangulation, that's the only thing I need to have in my about block. That means it will be higher in search results when I search for constraint Delaunay triangulation. And interesting thing, it works instantaneously. So there is no, it's not cached. Apparently, it's somehow. So you just change the about block, you do the search on GitHub, and you see immediately that the order changes. That was fun. Yeah. Links on Wikipedia, I added them in relevant articles about Delaunay triangulation and constraint Delaunay triangulation. It's licensed under MPL 2.0, and I kind of like this license. It's neat, and it combines like good parts of BSD style licenses and like copyleft like GPL style licenses. So it's permissive, like you can use it any way you want, but it's also copyleft. So I developed this, I open sourced this. If you want to improve on this, I mean, you can't log this knowledge. It belongs to the public, so I think it's a nice license. And then when it gets the traction and you actually get contributors and bug reports and everything, that's great because it just helps you to achieve something you will never be able to achieve by yourself. So huge thanks to all these people and more. Probably I forgot some. There were finding bugs, fixing bugs for me, suggesting the fixes, having great discussions, suggesting some ideas I could implement. They did benchmarking, profiling. It's good. Right, so what are the lessons I have for the library to become successful-ish? It needs to solve important problem that many people have, should be easy to use, and of course, I mean, being first doesn't hurt, or filling the right niche, like permissively licensed, doesn't hurt. The reason the CDT appeared, there was no alternative, so we had to open source it. Having a community is a superpower because it helps a lot in making the library better. Determinism is great for debuggability. If your problem is visual, if you're lucky and your problem is visual, make use of it, visualize it, because that also helps a lot to understand things and debug things and improve things. For example, like imagine this presentation without the images. It will be much harder to explain just with words. And invest in some tooling, internal tooling for the library, because it helps the velocity of debugging and maintaining. Thank you. I'm happy to connect if you can find me on GitHub or LinkedIn. And that's a link to the poll. It's like 2-minute, 1-minute poll. It's just the same questions I asked for the hand raise because I would like to have like the real data. I find it interesting. And then you can also rate how you like this presentation. Thank you again.